Hi, everyone. So we are here in a new session of the On Linguistics. We're happy to invite Professor Perrini Brusini from the University of Liverpool, Department of Psychology, the Lucid Center. Hi, Perrini. Thank you for being here today.
Hi, thank you for inviting me.
Okay, so today Perrini's talk is going to be about. Can you show us the screen, please, with the presentation? Thank you. Okay, so the title of the talk shall be multi-level linguistic analysis using neuroimaging. So I hope you enjoy it. Perrini, you may start. Thank you.
Thank you, Marília, and thank you to having me today here and to participate to this talk. I just wanted to spare 2 minutes about what is happening in Liverpool right now, because I would like to emphasize the fact that we are in conflict with the management. So we are on strike right now. I'm on strike, but I didn't want to cancel this event that I'm very pleased to participate and don't consider that the management have anything to do with. But the university have decided to sack my colleague of the department and fire them during the pandemic. And if you want to know more about, look at the union pages, but it's all about this. I just wanted to pop out this issue that is very close to my attention right now. So let's start with this talk. I have a little introduction that probably will not be so interesting from some of you that know a lot about language, but I wanted just to be sure that everybody starts with the same knowledge. So language is a very complicated stimuli that we use in everyday life, but when we have a discussion, in fact, we must recognize words, sound, and all of this goes super fast. So I found an images on Google that describes the sound sequence. So this is a signal on the oscilloscope. And inside this sound sequence, we should recognize the sound of our language, track the order of the sound and make them into words. And we should even try to decode the sentence using these underlying grammatical rules. So in my example that I found on internet, the presence of this auxiliary R here is dependent on the presence of this S here at the end of this word. So it's a very complicated signal, but we are in front of some kind of paradox here, because as an adult, we decode this almost effortlessly. In fact, I can do many things while having a discussion with someone, and sometimes pretty complicated tasks, sometimes playing a game. Anyway, so we have this on the part of adults, but there is another part, which is acquisition. This is the main domain I work in. And infants acquire all the need to decode this stream very quickly. So how is it possible? And how can we solve this paradox? So one of the possibilities is to find the cue that the language processing system rely on. So one of the possibilities of why, as an adult, I can process the language super easily is that there is some very important cue in the sound, in the speech signal, that I don't really realize that are super important for my processing. But as soon as I hear them, I understand what is going on, and I can go to the next task. We can describe the neural structure that supports the language processing. So by knowing how the brain is decoding the signal would be a good way to know how adults are so efficient to process this signal. And again, this will be a part that focuses more on acquisition, but a good way to know how infants can perform this learning as quickly will be to determine what part of this process might be the result of innate bias. So potentially, the human brain perceives sequences, and most of the time we use sound sequences in a certain way, we have a certain way to memorize a sequence that make language in a way easier to learn because it's the way the brain have been wired. And again, I will focus more on acquisition, but to make all of this possible, we need to know precisely when some of the processing that we need to do when you listen to speech are available for infants. This is really crucial. Why? Because you don't have the same mechanism to learn a language when you have another piece of information to process language. I will give you an example because I'm scared that this is not super clear. Let's say that you want to describe how infants learn the phonology of their language. It won't be the same mechanism that you have to describe if you want to explain how they learn the phonology, if you know that they have the lexicon of their language. It's not a plausible explanation, I agree with you, but it would definitely not be the same mechanism because if you know the lexicon of your language, you can infer the phonological rule of your language because you have this distribution inside the words. So having this information is determinant for developmentalists to explain what are the learning mechanisms of language in infancy. And in this talk, I want to argue that the use of neuroimaging technique is here of very great help for developmentalists. And to make this argument, I will rely on a view of what the field of acquisition classically thought of a timeline of what an infant can do according to their age. So I took this image from a Kuhl review. So Patricia Kuhl is an excellent scientist that have done so much in the field. And I must also admit that for the purpose of this talk, it's potentially a bit old, but it was the only timeline that I found. But so let's look at this timeline. And so we have here an infant that will be from 0 to 12 months. And we have first our infants that start to discriminate the sounds. At some point, they are able to find the words in the speech, thanks to statistical learning, the use of stress. And they will slowly focus on the sound of their own languages. So that was the classical vision not so long ago. And in this presentation, I will show how neuroimagery have changed this vision in the past few years, so we can really update this timeline. What I will do is first present results focusing on word segmentation in 2 experiments. Then I will show that we need to add another milestones before the age of 1, looking at morphology. So let's start first with word segmentation and more specifically, statistical learning in word segmentation. So what do we know about statistical learning? Well, we have this very famous experiment by Safran et al. It's from 1996, it's published in Science. And what Safran have done is to create a stream of synthesized speech where the author have manipulated the way the syllables co-occur together. What does it mean? It means that they have formed words in a way that they have a distribution property. So the syllable of a word will always appear together. So they have a TP, transition probability, of once one of the syllables appear, you are sure to hear the full words. While the transition of probability between the words, when you cross the boundary of a word, you have a drop in the statistical probability, the drop in TP. And what they have found is that when you present a stream like this of 3-syllabic words to 8-month-old infant, is that they are able to use this statistical information to extract the words. So this is a very key experiment for the field. But since, of course, it has this result has been extended to many other aspects. So we can do this with non-linguistic stimuli, like tones, for example. We can do this also in a visual domain with shape. Even rats are sensitive to the distribution of syllables, so it's not specific to human at all. And there have been some work with neonates that show that there is some sensitivity to the distribution of syllables or tone, and also some images. But there were, until recently, no clear demonstration that show that newborn can extract and memorize words just using the statistical information. And for the experiment that I have realized with a colleague of mine, so Anna Flo and Al Safari, we have used a machine that is called F-NIRS. So in case you know already about this, I'm sorry, that will be a bit boring, but I just, again, wanted to be very sure that everybody follow what I'm saying. So what is recording a NIRS? The NIRS is a machine that uses infrared, so that's what it says, near-infrared spectrometry. So you basically send a red light at the surface of the head. And what you want to look at is to find if on the surface that you are recording, there is oxyhemoglobin, so a very light red blood, the one that are full of oxygen, or the deoxy blood, the one that are deprived of oxygen. So this is the signal that we have here. And we have the signal here for the oxy that is going up. It's describing the neurons that is working. So why it is describing the neuron that is working? When a neuron is working, it needs nutrients to produce electricity. But if you have finished its reserve of nutrients, but you are still demanding this neuron to work, so for example, if you have a long conversation, you might need the neurons that process language for a long time. It will require new nutrients, so it will kind of call more blood to itself. So you have this shape of response that is close to the bold signal that you can record in MRI if we are not too precise. So this is the signal that we are looking for with the NIRS, is looking at places of the brain that have very high color blood, if you go a bit broadly. So what we do is that we have a source of the light, the source of the light that is sending the light, and we have this kind of banana shape flux that is going back to the emitters. And what we want to know is what is the level of this red light that have been absorbed when it went inside the cortex. So this technique has advantage and disadvantage. So one of the advantage, it has potentially good localization. I want to put potentially in quotes. It's because, well, when you put your channels on the place of the brain, you know that you record the specific place where the channel is. But without anatomical information, you don't specifically know what part of the brain you record. Of course, if you place yourself on the frontal area, you should not record too much from the visual area down the back. But what anatomical part of the brain you record is a bit less precise. It's non-invasive, so it's really not dangerous, so it's totally baby-friendly. And very importantly for us that work in language, it's silent, which is not the case from MRI that make a lot of noise, so you have to cover the ear of your participants, etc. But it has also some issue. Well, it's not too sensitive to movement, but sensitive enough that when a baby is moving too much, you lost your data. The light is not going, obviously, very far inside the cortex. So you really record the surface of the brain. And well, as I said, with this technique, we have no knowledge about the anatomical information of what specific brain structure we record. But it's very useful, and we can use it, for example, with newborns. So here I show you some picture of a newborn participant that we have welcome in the lab. So what we do is to place these different probes. So the blue are the receptor, the red are the source, and we place approximately the probes according to the mastoids there from the baby. But that's where you can see the approximate of the spatial information, because the shape of the head of a newborn is so different that, well, you record approximately the same things, but you cannot really argue that you have recorded a very precise structure. And this is the placement of our probes put on a schematic head of a baby. So as you can see, we aim to cover the frontotemporal area, which should be the part that approximately is concerned by language in newborn. But so the next question when you have this presentation is to know what you can do with this technique. Well, you can use it to record brain area, like cross brain area. Like if you want to know, for example, if something has been processed by the visual area or not, you can place your probe around here. But it's not really the way we have used it in our team. And so the experimental design that we have used, and I will use it 2 times, so I want it to be very clear for you, is to use an habituation paradigm. So the habituation paradigm is something that is very classical in the infant literature, and you can, in fact, use it also with neuroimagery. So this is what have done a previous team, Nakano et al., that have looked at the processing of syllables in infants. And what they have done is simply to repeat one syllable, so pa. So here you have the first instance of this pa. So the brain is really reactive. So like you can see by the red on the channel, there is a lot of activity from the brain. Oh, there is a new sound. This is interesting. But when you start to repeat this pa again and again, well, the activity is decreasing a lot. So it's not interesting. Your brain, the response of the brain are slowly going down because it's require less effort to process it. So if you present again the same syllable, well, it won't really wake up this. So this is like an habituation response. You're, okay, I know already this, this is not interesting. But if you present something new, so here we change from a pa to a ba, well, you go back to this big activity, so the brain is interested. So it's exactly the same thing that what we do with the behavioral paradigm. So this is, in fact, exactly what have used saffron in the classical experiment. There is a long stream of habituation, and you present some part of this habituation and see what part of habituation are like, okay, I've already heard that, or, oh, this is new. So you can really interpret these results as some kind of behavioral result. So here, the increase of the response is assumed to mean novelty. So it means I have detected change right now. This is new. I haven't been exposed to that before. The advantage of this is that it's show a massive response. So if you don't record anything, it means that your baby have really not perceived any change. So this is really massive. The disadvantage is that we cannot rely on any kind of clear localization for this. As you can see, the response of the brain is massive, so it's coming from everywhere. You cannot really say, this is the part of the brain that have worked to do this. But now we can develop some solution to this, and well, I keep that for the very end of my talk. So what have we done with this NIRS experiment? So okay, so we have done this. So we have put an habituation phase, in saffron, so a stream of 3.5 minutes. And then we have presented some test block where we have presented in isolation, so the word that are defined by the statistical rule, and the part word. So what do I mean? So inside the habituation, we have presented this stream. So it's complicated for me to share some sound here, but I can play you how it sounds. It's totally flat. So mi, pe, du, fo, gu, lo, be, fi, te, vo, canu, lu, go, la, vo, canu, etc. and etc. You understand the gist. And the way that this stream has been done, so it's a synthesized speech. It's to create the syllables and put them together in a way that a word is defined by having a one transition probability. So you can see with the big arrow as the one with the one probability. So the statistical word on this schema are the one that have different colors. And you can see that between a word, so between this word and befite, you have a smaller transition probability. So it's a difference between 1 and 0.33. And so you have this long phase of habituation, and you have a test test block where you present either the words or the part word. So the words are the one that we can see in color here, and the part word are made from the two last syllables of a word and the first syllable of another word. So exactly what is highlighted here. So what is interesting here is that the sequence of syllables that we present in test, the word and the part word, are effectively presented in this order during the habituation. So all of those are sequences that are present during the habituation. And so the question is, if you present these sequences that are effectively present, but cross the boundary of the statistical regularity, does infants perceive these words or this word during the habituation? So what do we expect? If the newborns have extracted the word, the statistical regularity, they should have an habituation effect when we present the test block. When we present the part word, we should find a novelty effect. And so the habituation effect is a decrease of a deoxy response, and the novelty effect is an increase of the novelty of the oxy response. And we have tested in this experiment 40 full-term neonates. So neonates here means 3 days. So a few days after birth inside the maternity. And so here are the results. So what I show you is the result of the cluster-based permutation analysis. I don't want to go into the details of this, but the way you have to look at these two figures is that on top, you have a time plot of each channel. So the first line here is when the block of test is starting, and the little line here is when the block is ending. You have the word in the plain line. The red line is the oxy, the blue lines are the deoxy. Let's focus on the oxy response because that's where classically we have the best signal. And the part word are with the dotted line. And as you can see, the dotted line is almost systematically above the plain red line. And the part of the graph that have this, it's in fact little stars that are put very close to each other. So that looks like a line as the one that we find the significant differences. And on the bottom, you have exactly the same result, except that we have take out the time effect. So you have our channel are the nearest, and the probes that have a statistical difference are the one with electrodes. So this is by doing the part word minus the word, so that's why it's positive. And so this is an analysis that is very specific to time series, the cluster-based permutation analysis. But we can use with this data a more classical way of analyze data, so an ANOVA. And here you have in pink the part word, in green you have the word, and as you can see, the response for the part word is really an increase of deoxy compared to baseline, while we have a decrease compared to baseline with the words. So what can we conclude from this? So we observe an increase of oxyhemoglobin response when presenting the part word in the test block with newborns. So this is indicative of a detection of novelty from the participants. So the part word were new from them. They were saying like, oh, I was very bored by this memorization at the end, but now they present me something new. So this is more interesting, let's say. Which means that the words were not new, which basically mean that the newborn have used a statistical regularity to extract the words. It also means, obviously it's not a long period because the total length of the experiment here is 13 minutes. But it's for the first time, the demonstration that newborns can memorize sequence of words. So for a few minutes, we never test longer than this as a newborn. We never ask them to come back to check. But let's say that they have, even if they have forgotten this after the test, we show here that the basics of extracting words is there at birth. So we can really, in fact, argue that from the very first days of life, newborns can start to learn. Do they memorize what they learn? I cannot say, but the mechanisms is there from birth. So if we go back to the timeline that I show you, the one that is published in the Cool paper, we have the statistical learning that were placed at 8 months. And in fact, we can totally correct this. No, it's happening during the first days of life. And I want here to really emphasize the fact that without neuroimaging technique, this result wouldn't have been updated. Why? Because newborn is a very, very difficult population to test. Most of them need to sleep a lot. They have very short period of wake during the day. And the span of things that they can do, if you imagine at some behavioral technique with gaze or head turning, it's not possible to test them with this technique because they don't have the capacity to direct their gaze properly. So without neuroimagery, we wouldn't have been able to update this result. But this is not the only result I want to update here, because I don't know if you noticed, but there is another thing here at 8 months. It's a detection of typical stress pattern in words, which is another cue that you can use to segment speech. So the question that you can ask there is that, well, you use statistical learning to segment speech at birth, but you will wait 8 months to use some other information, so the prosodic information. So I guess you understand that now I will present you another experiment with word segmentation, but using prosodic information. So what do we know about the prosodic information processing? So prosody is already a bit, is kind of an umbrella term that describe different acoustic realization. The first big paper in word segmentation that shows the importance of prosody to segment speech is the paper from Johnson and Jusick. And what they have done is to replicate what Safran and Hall have done. So they use a statistical information to create a stream. And they decided to add the stress cue. So stress It's very important in English. It's something that I don't manipulate very well as a French person, but you are supposed to put the stress on the first syllable of word in English. And what they have done is to pit these two cues. So they have created a statistical word with a TP of 1. So each syllables always follow one other in one word. But if you cross the boundary of a word, you have a drop of statistical probability. But what they have done is to put the stress on the last syllables, which is not something that you're supposed to do in English. And they expose to this the 8-month-old, and they wonder if the 8-month-olds will follow the statistical rule, so the one that show the stress at the end of the third syllable, or if they have follow the rule of English and use the stress as a segmentation cue for the first syllable. Well, for this result, 8-month-old have followed the language pattern. But there is many other prosodic information. So there is the phrase prosody, the contour. And what we know is that for infants and adults, word extraction is facilitated when you put them in accordance with this prosodic boundary. There is also some apparently perceptual bias that operates on language, but on sound sequences. That is called the iambic trochaic law. I'm not a specialist, so I prefer to not enter into too much details, but I think that some papers have shown that even rats are sensitive to this law. But there is, again, no clear demonstration that newborn can use this supra-segmental information, so the one that we add on the sound, to extract words. So that's what we wanted to look at. So how we do that? Because we want to use, again, standardized speech to control very well what we present to the newborn. So the lead of this experiment, Anna Flo, what she have done is to record an Italian speaker. So that was back when I was in Italy. And she recorded different sentences, so short three-syllabic sentences like ti pare, si vede, come va, and use the contour, so the specific shape of the rhythmic that you apply on each syllables, and extract it to superimpose it on the words that we created with the speech synthesizer. So I'm very bad at this, but if I try to copy the come va contour, it will look something like Lugola, I think, something like this. But if you go to the page of the paper, you will have all the sound available. I think it will be better. Anyway, so the set of stimuli was used in with the same idea, with the habituation. I'm mad with the U apparently. Habituation paradigm with an ears. So in the habituation phase, we present for 3.5 minutes. So there is a little change here. We don't want to have statistical information. We don't want that the baby can rely on this. We know that they can do this already. So what we have done there is each word are concatenated always at the same place. So it means that the TP, the transition probability between the syllables, are always 1 because there is no other effect. And again, we have test blocked where we present word and part word in the relation. But there we have an issue because the signal of the word and the part word are not the same during the habituation because we have the prosodic contour. So we decided to present them flat. So there is a difference of signal, which is important to remember, between our test block and our habituation block, which was not the case in the first experiment. So again, I can show you in more details what it looked like. So we have a big habituation period. We present the words in the same way. So the only difference is that we have the prosodic contour, and as you can see, the order is always the same. So the words that are described with a different color come back always at the same order. And the same exactly, we have the word and the part word, and what we expect if infants use the prosodic contour to extract word is that they show a novelty effect for the part word, so an increase of the deoxyhemoglobin, and habituation effect on the words. And exactly the same, we have tested 40 LC neonates with the same, approximately the same mean age. So again, this is the same way to present the results. We have used a cluster-based permutation analysis. We first show here the time plot of each channel that we have in our near systems, and a map of which channel was statistically different between the part word minus the words. And as you can see, we have a positive differences. And here also on the graph, the dotted line is really above the plain red line. And the difference are found statistically significant with the cluster. And we can also extract the data and average it to do the more classical analysis, so in the ANOVA. And well, what is slightly interesting to see here, which was already the case if you were super attentive here, is that we have our effect, but only on the right hemisphere. There is not so much happening in the left hemisphere. It's interesting, but we don't, I mean, it's interesting because many papers in adults show that the music processing, the one that could be the closest to what you process with contour, is mainly processed in the right part of the right hemisphere in our brain. So obviously, again, in this technique, when you use habituation, it's not the best way to claim anything on the spatialization. But it's at least coherent with what we know in adults. So what we can conclude from this? So we have, again, observed an increase of oxy signal when presenting the part word. So again, this means that our participants have found that the part word were a new signal when exposed to the test block compared to the words. And I want here to remind you that both the part word and the word were in fact new because they were flat. So during the habituation, we had the same syllables, but with the contour. And during the block, we change the signal. So for the brain, it's not the same signal. But even so, it was not the same signal. The part word were even newer, more new than the word. So from this, we can conclude that the baby have used the prosodic contour to find the word's boundary. And even more impressive, we can see that newborn can generalize the suprasegmental information to the phoneme thanks to this difference between the test being flat and the habituation being non-flat. So I want to come back to my timeline. And well, I know that I kind of tease this by speaking about stress pattern, and it's not exactly what we have tested, and we didn't have time to do this. It would be interesting to see if it doesn't appear earlier, but what we can add this definitely is that the newborn can use the contour to extract words here. Again, without the help of neuroimagery, I'm not sure how we can really find this. I mean, maybe some people are very, very smart to imagine situation of test in which you can have the response of a newborn. But honestly, I think that neuroimagery here is a very, very useful tool to test this very young population. But the question that I will ask to follow up on this talk is there any other kind of ability that is missing here? And I want to emphasize this because we are looking here at the first year of life in infants, and specifically in the lower part, so this part here, it's very difficult to test the infant in the classical behavioral paradigm, because even the head-turning paradigm can be a bit complicated to learn from infants. So this will be interesting to look at other aspects of language acquisition. And I will ask a more precise question. So we can see here that I have 9 months. We have the recognition of language-specific sound. So if 9 months can recognize the language-specific sound, are they able to attribute this sound to a specific meaning? So what I'm going to is to look at morphology. So what do we know about the learning of morphology in infancy? So first, if anyone is confused, what is morphology? Morphology is a subpart of language. So when you learn language, you need to do something very important that I mentioned earlier. It's to find the words. And when you find the words, you need to link them to some concept. And apparently, infants can do this before the age of 1. But it's not the only things that only sound meaning that they have to do, because when you modify a tiny bit these words, you change the kind of concept that you speak about. So for example, if you add an S to the word apple, you will not speak anymore about one single apple. You will speak about more than one apple. So 2, 3, and etc. So this is another rule to learn for infants. And we can wonder when they start to do this, because many languages use morphology, and some languages use many more morphology than English. We know that infants can detect regularity pretty early on. Well, there is an experience of Marcus about this, for example. But when do they really learn morphology? So attribute a smaller language unit to a concept that is potentially more abstract. In English, a paper, I found that it's kind of late. It's about 20 to 24 months old that they start to understand the plural. So there is no gender that is easily marked in English, apart for the subject pronoun. But so if we put aside English that doesn't have so much morphology, we can wonder if in other language we have different timeline, because potentially the way a language express its own morphology can differ. So for example, we were in Italy at the time, and Italian is a very, very rich morphology language, and there is a really robust morphology. So it marks the gender and the numerals. The variation is very consistent across the different use. And the marks are present in many words of a signal. So you have the article, final vowel, you have the adjective, the past participle, and of course, the nouns. So here I got you some examples of this. So for example, if you say la bambina, you will speak about a little girl. if you say le bambine, you will speak about many little girls, so more than one. If you say il bambino, it's a little boy. And if you say I bambini, it's many little boys. As you can see, it's pretty systematic, and you have some kind of root that focus a specific age range, and you have other words for a different age. So you have adult and elderly, and the same rule apply. You change the article, you change the last vowel, and you change basically to who you refer to. So the question that have been asked by Alisa Ferri when I arrived to the lab is, does Italian infants learn this early on, because it's so systematic? And so she started to test 24 months old, as it was the age at which English do this. So it was really not an issue for the infants. And so she went lower and lower, so 18 and 12. They all do this super easily. But I want to focus on how she have done this. So the way she have done this is this listen while looking paradigm, in which you present two possible images, so they are in opposition, and you present a label to these images. So either you will have guarda la ragazza, which is look at the woman, so you expect people and participant maybe here to focus on the lady here, or guarda il ragazzo, and you expect to focus on the other one. So you use an eye tracker most of the time, and you record which part of the screen the infants are looking at when you ask them to look at a specific image. And well, I will present you first the result. First the result. So this is the result. So the 0 is made about the baseline. So basically what we're recording here is an increase of look to the correct images after the label. As you can see, the 0 is here, the mean of each group is here, and everything is significant. So all the ages have done this. So, and well, even so, the 12 months old show a bit more spreading. Each dot here are a participant. So for some 12 months old, this was a bit difficult. But still, at the group level, they do this. So she lowered again the age, and she tested 9 months old. But the 9 months old failed. And I will go back to the paradigm here. So it doesn't look very difficult, of course, for an adult. But when you are a 9 months old infant and you are exposed to 2 new images that you have to look at and to really understand what are the difference between the 2 images, and then listen to a voice that is giving you instruction and control your gaze to properly choose which image to look at, it is pretty difficult. So basically what I'm saying is that the executive function of a 9 months old may not be at the level of what is required in this behavioral experiment for them to show off their linguistic capacity. So the question that she had after this fail in this experiment was, is this a real linguistic fail? Is it that the 9 months old haven't learned at all what the morphology mean? Or is it the fact that the paradigm here was originally made for 24 months old, so 2 years compared to 9 months? And that's approximately the moment that I arrived in Trieste. And so Alisa Ferri proposed me to collaborate with her to do a EEG experiment. So this is what I have been first trained is to do electroencephalogram with infants. So the electroencephalogram is this technique where you put electrodes on the head of a baby. So when you say electrodes, it can look a bit scary, but it's really not dangerous. It's only record. It's totally safe for infants. And what you do is you record directly the electricity that is produced by the neurons when, well, adult or infants process something. So it can be visual, but, well, we are focused on language here. And what is happening when you record EEG of infants and you present an images? So, for example, you show them one of these little duck toy, and you say, look at the ball. You record a specific effect that is well documented in EEG, maybe one of the most described in language, which is it's called the N400. So it's this kind of an error signal. Basically, the way you can interpret this is that, well, I know the label of this word, and this is not a ball. This is a duck. So the principle of this is just to present one images. So we can see we reduce the complexity here of what we present to infants. And we present a sound that either properly describes the image. So la ragazza is the lady. Wow, le ragazze. So here it's a mismatch, but you mismatch on the numeral. So you speak about many ladies. And il ragazzo, so here you speak about the man. And what we have done here is to start this experiment with 9 months old. Well, in fact, we first tested adults just to check that everything was working well. And then we tested a lot of 9 months old infants. And here are the results. So first, to explain the results, I need to tell you a bit about the timeline of this experiment. So here we have first a moment where the participant, it was for infants, have a long time to look at the image and really consider what was the physical property of each image to decide what gender was the image of. Then you have a little, what we call carrier sentence, when we say, wow, guarda, oh, something like this, to encourage the baby to look at what we are describing. Then we have the article and then the label. And we decided to put the 0 on the article because, well, Italian is made in sort that we repeat the information. So at the end of the article, we already have some cue of what is the gender and what is the numerals of the noun that is upcoming. So we wanted to see if by any chance there is already some response here, and we wanted to see, of course, if there were responses that correspond to the label. So we have almost 2 timelines of interest. But as for the NIRS, what we use is this cluster permutation analysis. I can come back to this if you want, but again, this is not the purpose of this talk. And we compare the congruent, so we put all together all the trials that describe well the images and all the trials that didn't describe well the images. So first, I show you the adult response. So what I'm showing you right now is, let's imagine that this is the head, but view from the top. So this is the nose, the ears. And what I show you is the differences recorded for each electrode when you do incongruent minus congruent. And when you do this, you might record either a positive response, so this is on the red on this scale, or a negative response. And here, in fact, I'm showing you the electrodes that are statistically different with the cluster permutation. So what I'm saying is that between 150 and 400 milliseconds, the adult displayed this big negative response. So here, it's an average between this time, which really look like an N400. So some people might say, well, it's not totally an N400, and I will say yes, because it's not properly the good time. But consider the fact that the adults have 2 seconds to look at the visage, the face of the person, and well, there is the article. And so the 0 is really the end of the article. So for the adult, this experiment was easy. So we are not very surprised to record early N400. For the infants, it's a totally different story because we don't find anything with a cluster before 750 milliseconds, but we find something significant. And if we come back to this timeline, so it means that after the article, where there is not so much, so it seems that the infants cannot really exploit the information that is on the article to decide if the label will be good or not. But at 700 milliseconds, well, we are about 300 milliseconds after the end of the label. So it means that this response is very corresponding to the timeline of the N400. And well, it's negative. And well, the topography is resembling of what Chibra and Parise and all are found. And well, even so, this positive things is really showing up on the average. On the cluster is not significant. So we consider that here we have records expected answer, so the N400. But we have some kind of other response with this paradigm. We wonder if the 9-month-old really knows the morpheme of Italian. So the question was, well, when I use a, so the a bambina and mean girl, or o bambino, do they really know that the a is for the girl, the o is for the boy, the a is for girls, etc. So we wanted to look at the detail of this response. So what we have done is to extract the data that the cluster have found, so the electrode inside the time that the cluster have point out. And we average this response and look at the different conditions. So first, I'm showing you the congruent response, the incongruent response when we change the gender. So basically, you see a girl, but I speak about a boy. And the number, so basically you see one person, but I mentioned two. And well, as you can see, there is some tendency here, but well, when we separate these two conditions, we lost our statistical power. And you won't be surprised if I tell you that if we look even smaller, so if we compare the feminine singular to the feminine plural to the masculine singular to the masculine plural, well, we cannot really say much. Some tendencies that we can observe, but unfortunately here we really lack of statistical power. Well, one of the reasons that this experiment was a bit complicated because even 9 months old was pretty bored at the end of the experiment. So they have to watch the screen and listen to, wow, la ragazza, next trial, a girl, wow, il ragazzo, etc. and etc. So, and our lab was closing in Trieste, so we really tried to do the best with the data that we had. But what can we conclude from this experiment? Well, I think that we have good basis to say that 9 months old infants know something about the morphology of their language. We cannot say much about if they really can map each morpheme on the concept that they link to. Unfortunately, it was too many conditions for the statistical power that we can develop here. But it shows that as soon as 9 months old, in Italian, infants have some knowledge of which morpheme is supposed to be used when you speak about a girl or many girls. So this is very different from English, for example. So here we come to the fact that from studying different language, we can in fact maybe expect a different timeline of acquisition. So potentially, the input that the infant receives is shaping differently the way it will develop, the way it will learn the difference in its own language. So I will come back last time to this timeline that have been created by Cool. So as you can see, we have put back here statistical learning, we have contour, we can have a little question mark about the stress. And well, from the last experiment, we can add something that, that look like this, like potentially at 9 months, if your morphology is consistent, so sorry, it's me writing with my mouse, so it's very ugly. Morphology, if consistent, it's possible at 9 months, and well, Alisa Ferry showed that they know it perfectly at 12. And so again, this result wouldn't have been able to be found without the use of neuroimagery. So as I said, the executive function of all the infants that are in the lower part of this chronology is bad, let's say. So even eye tracker have difficulty to record the eyes of very young babies. The fact is that the eyes of the baby have very watery, so the pupil is less obvious by the algorithm that use the eye tracker, so this machine that focus on the eye. So again, I want to emphasize the fact that neuroimagery is very useful, but I think I will pursue this in my general conclusion. So we saw in this talk that neuroimagery is a very useful method for all the developmentalists in a way that they can set up a new paradigm to look at what infants really know in language during development. So why? It's because, as I've shown, it allows to test infants passively. So what we can do is basically record the brain of infants while they are processing their inputs almost naturally, without asking them to do something complicated, to learn a task or to make movement with their head, etc., etc. But well, I'm a big pro of the neuroimaging technique, but I want to emphasize the fact that it's not magic. So if you have a good behavioral experiment that you are sure that you will have the result, don't really jump onto a neuroimaging technique because, well, it's difficult to test infants with neuroimagery. As I said, the techniques are perfectly safe, but infants, they don't really appreciate to have something on their head. So you have to place the probes, you have to touch the head. Some age it's a bit difficult. The EEG cap, the one that I'm used to use, it needs to be wet. So you put them in the water, so you place a wet hat on the head of a baby. Well, you need to record many trials without artifact to be able to exploit your data. We saw this with my last experiment. So it's not a magical technique. And if there is a pretty safe behavioral method to use, I think the best is to potentially use the behavioral method. If you look at the participant description in neuroimagery technique, you will see that we drop a lot of baby compared to the behavioral technique. It's because, well, if a baby moves during the experiment, it's life. You cannot say to the baby, you should not move during the experiment. So, well, so we can remember this about this talk. But, well, there is a little addition that I want to show you quickly to the end, at the end of this talk. That's bringing neuroimaging data. So I want to show you quickly how you can exploit further the neuroimaging data. So as for now, I show you almost the use of neuroimaging data as we will do a behavioral experiment. So basically, you do an habituation, and you look if you have an error response. But you can exploit them very differently. So what I've done, Anna Flo from Sexta, so the colleague with who I work on this word segmentation experiment, is to take the habituation recording of the brain of the newborn and starting to think, well, if you learn some things, it means that your brain is changing. The way your brain coordinates itself to process this will have to adapt to extract the pertinent information. So what it means is that you can look at the area that work together. How does it look on your data? Well, you remember with the ears, we have this kind of setup of channels around the head. And well, we can look at the one that work together. So basically the one that have an activity that correlate, even positively or negatively. And you can look of how they do this across the timeline of the formalization. So basically, you can look at the neural network that is doing the work to do the learning. So this is the first network that Anna have extract from the data. It's not a very interesting network, and we suppose because it doesn't change according to what the baby hear. But so we suppose that it's just like a blood functioning, breathing network. But there is other network that can be exploited from that, and those networks seems to work as small words, so meaning that you have center hubs that do the big processing and share the information with a different part of the network. And this network change if you present a statistical stream, so the one that I presented, or if you make the syllable random. So you present the same syllable, but they have no structure, so you cannot extract any words, or even silence. So here, it starts to be very interesting to exploit this neuroimaging data, because we can potentially see the network at work, so really specific to the task, specific to language processing and potentially language learning. So that's all I wanted to present. So many thanks for your attention. I wanted to pop out the fact that all this work have been done with Jacques Meller, that is really missing to science today. And well, from my two wonderful colleagues, Anna Flo and Alisa Ferry, when we were together in Sexta with Jacques. Thank you very much.
Thank you, Perrini. A great talk on behalf of the graduate program of linguistics of the Federal University of Rio. I thank you. We have some questions, so let's start with, there is a question from Frederico Torres Ludigero, and he asks, would these findings apply if it's a second language acquisition? So I think when you were talking about morphology, for example, do you think that could go to second language acquisition? Bilingual, well, I think because you're so old, we're thinking of bilingual first language acquisition, right?
Yeah. Well, I mean, I'm really not a specialist for bilinguals. I mean, it's a subject that I'm more and more interested to, because it's also another, way to separate your brain, and you have to focus. And I honestly wouldn't try to make hypotheses. I think it's we need also to know what bilinguals can do, because it says a lot about what is the mechanism of learning in infants. What I know is that there is some delay at the beginning of life in bilingualism, so I wouldn't be surprised if potentially, like for morphology, for example, there is, differences. And what we have learned with this experiment is that there is also differences according to language. So what does English, for example, English, Italian baby will have to learn? So learn that in English, gender doesn't matter almost. That morphology is just this little S that appear once in a while. This, this is this is a very interesting question, but I don't know. I'm sorry.
No, it's okay.
It's the work of someone else. To do it.
Okay, thank you. Okay, so we have another question by Daniela Cid Garcia. Very interesting talk. Do you think that the segmentation study using TP could be replicated in more agglutinative languages? I understood these findings are using no more than 3-syllable words, correct?
Yes. So what we call the classical saffron experiment is really what we use the 3-syllabic words. There is few experiments out of there. Like for example, there is J6 have sometimes used bisyllabic words. And well, I will say that developmentalists are sometimes a bit superstitious. So we know that the 3-syllabic word works, so we pursue to use it. It's very questionable. For example, in English, the 3-syllabic words are rare. So this is potentially a bigger effort for adult, for example, when we do TP with adults. I don't know of any experiment of agglutinate languages. And honestly, so that would be definitely interesting. I think that there is few experiments out there that have tried to do bisyllabic words and 3-syllabic words. But we need to. There is still a lot that can be done, especially with infants. So. Yes, I think that we at some point should agree that the 3-syllabic words is not the best to describe what is really happening. But well, it's already a good cue to know what is possible from the language processing system.
Okay, and then there is a follow-up question by Daniela as well. How earlier can we use nears in relation to the sucking, the pacifier sucking paradigm, right?
Paradigm. So as far as I know, so I never use a sucking paradigm. As far as I know, the sucking paradigm can be used in the first few days of life as well. So there is no difference, I will say, as early on. But I never use a sucking paradigm myself, but my PhD director, so Anne-Christophe, was in the LSCP at the time where there was a lot of sucking paradigm method. And she said that for her, it was kind of a noisy paradigm. So I will not say that NIRS is not noisy because, well, each little movement of the baby. So for example, if you test the baby with the NIRS system and he has his pacifier and he starts to suck very strong on the pacifier, you will lose the data. So I will just say that it's another possibility. And as I try to show at the end of the talk, it's like another tool, but also another tool that you might do extra stuff with it. So like right now there is a new algorithm that are developed to do this this network in EEG. I don't know if you a bit less with NIRS, but there is in EEG there is a big exploitation also of the time frequency. That seems to be very interesting for language processing. So the frequency of speech are very different because the sound, the phoneme are very small units, the words are bigger one, and the phrase are even bigger one. And it seems that the frequency at which the brain are working, so the delta, theta, gamma, etc., correspond well enough to each of these units. So there is a bunch of paper from Popple, Giro, and other researchers that show that it seems to have something here that we can exploit again. So yeah, I will not say replace all the behavioral by the neuroimaging technique. I'm just saying there is this on top, and we can do really good stuff with it, so we can know more.
Okay, I have some questions myself.
Sure.
I was interested when you were talking about your results. I know you mentioned that results on topography are not very good with NIRS, but I was interested with the findings on the right hemisphere, right, and music for adults, and right hemisphere for the babies, right? So do you think that could relate to child-directed speech because it's more prosodic marked, and are they understanding it like music, or I mean, how?
I mean, that's the thing, is that since you don't have the behavioral response, you just notice that there is a difference. And where the difference is on the right hemisphere, that is classically, as you said to be the one that process more musical.
But do you think we could, for example, do you think that we could, for example, show child-directed speech versus adult-directed speech, and maybe we could find with NIRS, or it's too much of data?
I think that we record differences, but I don't know. I mean, I don't know if
what they would show.
Interpret this difference because the signal is different. But well, there is a very clever experiment that shows that there is something in the child-directed speech. So Alex Christia done a lot of stuff on IDS. But for this experiment, I don't know specifically. And well, some reviewer, when we were doing the paper, said, well, new fetus around, if I remember well, around 32 weeks of gestation, start to hear some stuff. So it's very filtered by all, the heartbeats, everything. But the contour is one of the things that will be the less affected. So one of the questions is, so not all the mother that we have tested was Italian speaking, because we were working at the border with Slovenia. But I mean, it's we cannot tell there. But yeah, I mean, IDS is important for infant, and if it's not important in the quality of signal, it's at least important to notice that somebody is speaking to them and not to another adult. So it's really attention gather.
Nice, thank you. I have another question. Yeah, I think it's a similar question to what Daniela already asked, because you're mentioning the difficulties by using the imaging techniques, right? And I was thinking, if you already have, for example, the best age to work with, for example, NIRS, usually you work with neonates, but then you wouldn't study, for example, 1 month old or 2 month old with this technique, right? But then EEG, you would use for older babies, but then there's the problem of moving. And do you think that there is like a best age for EEG?
Well, yes and no. So the fact that NIRS has been used with neonates was kind of inherent of our lab, because we have the facility inside the maternity, so we have access to neonates. And Jacques was a very big nativist, so he was really wanted to do something with neonates. So it's not that NIRS is not possible to use with older kids. So there is a lab in Princeton that is doing interesting stuff with NIRS right now. it's true that depending on the nearest that you have, the power of the light will be different. And so neonates have almost no skull. So the light can be so we had old nears, you know, like so the light goes easy in the brain. Yeah, exactly. So if you test adults, you need to use a stronger light, but there is some lab that use nears as well with adults.
Okay.
But yes, so for example, I use mostly EEG because that's really the technique that I know the best. Even so, I learned with Anna when I was in Trieste with NERS. And this is time series, so but anyway, when I think of doing an EEG experiment, there is age. I know that once the net on the head of the baby will be more challenging than other. I think that you have also this experiment.
Yes.
So, for example, my first experiment was with 24 months old, and I test also 18 months old. And I think that someone has really to tell me the importance of this experiment to redo an 18 months old EEG experiment. Yeah, because this is really challenging. So there is many days when you go to the lab, you have participant coming and you go back home and you have no data. So yes, so right now I like this 9-10 months old because they are comfortable with stranger. You agitate a bit your hand and they forget that they have the net on their head. They can stand also properly, which is a bit more comfortable for you to place, you know, the net, because I worked with also 2 months old, and you know, their neck, so you are a bit less confident to when you put the net on their head. So there is preference of age, but I will say that age now is feasible. But yes, for some age, you need a bit more motivation, let's say.
Okay. Yeah, I think the point here, as you said, is not to think that it's magical, right? That because the results is just this colorful maps that is easy to get those maps, right? And
so, no. I mean, there is a bias to think that neuroimagery is more interesting, but I hope. I mean, again, there is this last part when you can exploit this a bit, you know, fancy way. But I hope you understand that in my first part of the talk, so the NEARS experiment and the EEG experiment, it shows the same thing that the habituation paradigm that we use classically with the behavioral method. I mean, there is no addition of the EEG, except of the fact that, well, newborn are hard to test, so it's very difficult to have a behavioral experiment. And the 9th month, with the technique that we have right now to see for the morphology, it was just the executive function that they have was not able to deal with the experiment. So we were not asking the proper question. We're not asking, are they able to do this linguistic stuff? Are they able to look at 2 images, which was not the interest here.
Sure. Yeah, this is important points. So I would like to thank you, Perrini. I think we don't have other questions, just people saying that the talk was great. So okay, so I think we are going to wrap up now. I thank you again, Perrini, and thank you all for being here. It was a great talk. Thank you. Bye-bye.
Bye, have a nice day.
Have a nice day. Bye-bye.